Hello Microprofessor friends, and welcome to the pinnacle of my series of YouTube videos about the force system for the Microprofessor MPF-1+. So this is really the final video, right? I know I said that before, but this is it now really. After that I don't have much more to share or to talk about the force system. So today I want to share my version of the infamous DOER and make constructs from the Thinking Force book from Leo Brody, right? And remember I mentioned in one of my videos that originally, like 3 months ago, when I started tinkering with the force system, I tried to implement a recursive version of the factorial function, right? And couldn't figure out how to do this. Iterative was easy using loop and do, of course, right? But recursive version took me down the rabbit hole, and I needed to learn a lot more force and the internals, all the stuff that we covered in the previous videos, CFA, PFA, how to do vectored execution. And then after some Google searching for recursive definitions in force, I then was referred to the Leo Brody book, right? And this, of course, has a definition of DOER and make in the appendix B, right? All right, let's talk a little bit about the return stack, right? I mean, all programming languages, of course, have one, if functions are calling other functions or procedures are calling other procedures, right? The calling function or procedure, or let's just say word, right? We are talking about words here. The calling word is called the caller, right? And the word that is being called is called the callee. So when the caller hands off control to the callee, before it does that, it puts basically the return address on the return stack, right? So when the callee finishes its work, it does a return, right? And it returns to the address that the caller has left on the return stack, right? So a simple example is, we write something like A, and all A does, it prints A on the display, right? And now we also have B. B first prints B on the display, and then it invokes the word, it calls the word A now, right? And at runtime, before actually calling A, right, it is putting the continuation address now on the return stack, right? So when A returns, there is an implicit exit, right, which is something which is automatically put into the definition by the colon compiler. So when semicolon is terminating the definition, what the colon compiler does, it compiles the call to exit into the definition, right? So the last word that's being executed in the definition of A is actually exit, right? And exit basically returns control to the caller, right? So because the caller has left the return address, which is pointing to this next word in its definition, right? So when A then exits and returns, control and execution returns at this point, right? And what I'm doing here is I'm putting in C, right? And again, now when B terminates its work, right, then there is an implicit exit as well. So it returns to whatever called B, right? So, and whatever called B, we are setting it up that in our case, test is calling B. So, and this is how it works in all languages, basically using the return stack, right? And note that the return stack is of course different from the value or ordinary parameter argument stack that we were using before, right? So we have not messed with the return stack before. But the return stack is basically, of course, required for passing control and returning from invoked words. So this is how this works, right? And now we can actually manipulate the return stack by hand, right? And let's illustrate what we can do. So remember I said at the end of each definition of each word, semicolon compiles exit into the definition, right? So and exit then just pops the value from the return stack, and control returns to that address, right? So if we put in on now arbitrary different addresses, right, then we can basically, when a word exits, pass control to not the caller, right, but to another word. And this is what I'm going to demonstrate now. So you have a lot of flexibility and full control, right? So I did a cold start, so I'm putting in A again, right? And now I'm putting in B again. But rather than calling A directly, what I'm doing now is I'm putting the PFA of A using tick on the value stack, the ordinary stack, right? And then I'm using this operator, this word here, which we haven't seen before, right? Which pops the value from the argument stack and puts it on the return stack, right? So this is only a shuffle from one stack to the other stack operation, right? So pop from the argument stack and push to the return stack. And this is doing nothing, right? This is not doing an execute, a jump to A yet. It only puts the address there, right? And so at that point, there will be no change in control, right? So the for system will continue printing C, right? But now, as I just said, the last word is an implicit exit, right? So when B then exits, what it does is it wants to return and it uses the top of the return stack, right? But at the top of the return stack is now not the address that the caller of B left there, but the address of A. So at that point, when B terminates, right, and does its return, it actually does a jump to A. So this is how we can actually, instead of using execute as we did previously, right, in the last video for vectored execution, we are now using the return stack to implement the calls basically to arbitrary positions basically. And of course you have to be careful with manipulating the stack, right? Because again, you can crash a system easily if you do something wrong. And again, we are calling B from within test. So what we expect to see now, if we execute test, right, we will execute B. B will then print B. It will then put the PFA of A on the return stack. It doesn't do the jump yet. Then we will see C. And now B terminates, right, and does its exit call. And the exit call doesn't find now the continuation here, but it will find now the address of A on the stack. So it will print C and then A, right? And then A will return, and now A will actually find the continuation which was left by the caller test when B was called, right? Because there's one more stack value. So then we will see test printed. So let's see if that indeed is the case, what I just told you, right? And there you go. So yeah, and note that of course there's a slight difference to the previous version, right? So because in the previous version we had the call to A in between B and C, right? So in the previous version, without the return stack, we were seeing B, A, C, right? Not B, C, A, and then test. And of course you can now do all kinds of funny things, because if you have control over the return stack, you can alter the flow of control basically arbitrarily, right? And of course that's dangerous, but also very powerful. So here's another example, right? So again, I did a cold start, A again, and now how about in B? Not only do we put the PFA of A once on the return stack, but actually 3 times, right? So when A is being called, right, for the first time, and it exits after printing A, it will find yet another call to A on the return stack, right? And it does that again, and when it exits again, every exit of course pops one value from the return stack. It finds yet another call of A on the return stack, right? And then finally it'll return to the caller. So in order to do this, same print B, right? Again, we are putting now the PFA of A on the value stack, and we are duplicating this 3 times because we want to make 3 calls to A now. And now we are pushing 3 values 3 times, you know, onto the return stack, right? And then again we are printing C, and then B terminates, right? Exit is being executed, and then it finds the 3 calls to A on the return stack. So what we expect now is, again, let's have test as a main function. function, word I should say. So what we expect now is we will see B, A, C, and then done, right? And there you go. And we can even drop values from the return stack, so we can choose to omit certain returns, you know. And let's demonstrate this. Again, I did a cold start. Here's A again, right? And now say that for B, we choose to not return to the caller of B. And for this, we can use, rather than pushing something to the return stack, which was this one here, right? We are now popping a value from the return stack onto the argument stack, right? So that's the inverse operation. And then once that address is on the argument stack, on the value stack, we will simply drop it. So the return address, the caller's return address left on the stack for B is gone. So when B returns, you know, it doesn't have that address anymore, the return address on the stack. So rather it is now, of course, printing B, and it's leaving again the PFA of A on the stack, and we are moving this over to the return stack, right, as we did before. Then we are printing C, and now when B executes, it will not return to its caller, right, and its caller is test, and so what we expect to see, or actually what we expect to not see, is done, right? So because we dropped the return to test, when B returns, or when A returns finally, right, it will not return to done. So we won't see done on the display. And there you go, no done, right? So, but you see that the system didn't crash, so it actually returned now to what did it return then, right? So we omitted one return to test, basically, on the return stack, but underneath that return, there was still another return address, right? And this is the interpreter. So this is why the system didn't crash. Alright, very good. Now that we understand the return stack and how by manipulating the return stack we can implement arbitrary flow of control, we see that this can also be used to implement vectored execution, right? And of course the last video was about vectored execution, and I showed you how we can use vectored execution in order to implement recursive definitions, right? We had a recursive definition of the factorial function as well as an example for indirect recursion, the classic odd and even example, right? And we had one defining word label, which was used to define and create vector variables, basically, right? And another word, rec, which would then be used at runtime to make a call to the address, to the code pointer stored in the vector variable, right? And that way we could implement arbitrary calls to, you know, forward references as well as recursive calls, right? And rather than using execute on the CFA like we did in the last video, right, with rec and the vector variable, DOER and make is using the return stack, right? And this is why we just covered that. So the plan is to, you know, use a simplified version of DOER and make, and this is what I'm showing you here, right? It doesn't support the full feature set of DOER and make from the book, but it's enough to implement recursive definition and arbitrary vectored execution, right? And so it consists of three words. So the vector variable defining word DOER, the compiling word make, right? And then the runtime semantics, which is compiled by make into the definition of the compilee, right? Is implemented by make with round parentheses, right? And that's the naming convention that the runtime semantics of a compiling word, such as make, is usually the same word, right? The same name, but with round parentheses around it, which is then executed at runtime, and that implements the runtime semantics of the compiling word. So that's just the naming convention. We could also, you know, name it comp make or runtime make or something like that. So And then we are going to key that in, right? And I've already keyed that in, and I'm sharing the definition of factorial here using that simplified version of DOER and make. And why is it simplified? Well, this is the full version of DOER and make according to the Brody book, right? And this has two additional features or words. One is and one is undo. I'm not going to explain in detail how these work, right? Or how the full version works, because you see it's quite a bit more complex. But I'm going to, at the end of the video, demonstrate that it works by executing an adopted and adapted example from the Brody book that also demonstrates and as well as undo, right? So just to show you that it works and to convince you that it's doing okay. So I should mention one more difference, right, to the make in the Brody book, right? So if you look at the definition of make in the Brody book, right, and how it is used, for example, for defining the greatest common denominator, GCD, right, as we looked at it at the beginning, you see that we can also use make on the interpreter level, right? Yeah, make on the interpreter level, right? Whereas the make word that I'm supporting is a compiling word, so you can only use it within a colon definition in compiler mode, basically, right? So we don't have a runtime version of make, but only a compiling word, make. But now enough with all the theory, and it's time to get hands-on and practical with our simplified version of DOER and make, right? Again, it's listed here, 3 words, DOER, make, and make for the runtime semantics. DOER being the defining word, make being a compiler word, a compiling word, having the immediate flag, and make in round parentheses, implementing the runtime semantics of make. So what make does is it actually sets the vector address to the right address, right? And we will see how that works, whereas DOER is used to define and create the vector variable. So I already typed it in and it's ready to be used, and we are going to implement this version of factorial here using DOER and make, and I'll provide some examples, some explanation along the way as I type it in, right? So let's start by defining our vector variable fact using DOER, right? So DOER fact, and let's have a look at the definition of DOER again. DOER is of course a defining word, and a defining word uses create to create new words, right? And it finds the name of the new word to be created to the right from the input stream, right? It reads fact, and then it creates fact when DOER is being executed. And it's also allocating 2 entries in the parameter field, right, using toAllot. So at that point we have created a word fact which has a parameter field of length 2. And of course this is where we are going to store the vector address, right? Because at runtime, when we are using fact to execute a jump to the vector address, the runtime semantics is specified behind does. So what it does at runtime is the value of the address stored in the parameter field is being retrieved using add, right? And this is being pushed onto the return stack. So the next time an exit is being encountered and executed, a jump to that address from the vector variables parameter field will result, right? So, and now, unlike in the Brody book where we could start now typing in make fact, right, and then the definition, start typing away, as already explained, my version of make only works in within colon definitions, right? So make is only implemented as a compiling word, but you cannot use make at runtime like this. You cannot use make in the interpreter directly. So rather what you need is you need to establish a compiler context, right? So invoke the colon compiler, right? And use a setup auxiliary word, right? Setup fact. So and now since we are within a colon definition of the auxiliary defining word setup fact, we can now use make fact, right? And remember how the colon compiler works. So usually for ordinary words in the definition, right, the colon compiler puts in the addresses of the CFAs to these words, right, if they are not compiling words. For example, if the colon compiler compiles the definition of setup fact, it goes through the words, through the definition. For example, for dub, right, it will put the address, the CFA of dub, into the definition, right, into the parameter field of setup fact, right? And at runtime, the address interpreter will of course go through the parameter field and will execute the calls which have been left there by the colon compiler, right? So the call to dub will be executed by the address interpreter by jumping, basically making a call to the CFA of dub, right, the code field address, and then when it returns, it continues here and so on. So, but for compiling words, right, remember we discussed these as well, compiling words have the immediate flag, right, and make is a compiling word now, so rather than the colon compiler is not putting in the CFA of make, but it's executing make right away, right? So at compile time, it sees, okay, immediate is set, it's a compiling word, I have to execute make right away, and then I do what's specified here, right? So, and what the compiler then does is it compiles the call of make in round parentheses into the definition of the compilee, right? So at compile time, all what that does is, right, this make compile time word is, it replaces this call basically with the CFA of make in round parentheses, right? And then of course, after putting in the CFA to make in round parentheses, the colon compiler continues compiling the CFAs of the remaining words in the definition, so it puts in the CFA of fact, the CFA of dub, and so on, right? So let's continue typing in the definition. After make fact, we gotta now start the definition, right? First we gotta duplicate the argument on the stack and check if it's smaller than 2, because if so, then it's either 0 or 1, and then we want to drop the argument in case it's 0 or 1, right, and just replace it by 1, which is the result then, because factorial of 0 is also defined as 1, right? Else we have the recursive case. What we got to do is, again, we duplicate the value, subtract 1, and now we can do the recursive call to fact, right? And here, of course, the colon compiler will again put in the CFA of fact, right? But at runtime, it then executes what's behind the CFA. It will execute this definition here, so it retrieves the address from the parameter field and puts it on the return stack, which then, when the exit call is being encountered, results in a jump to the address stored in the fact vector, right? And the address which we want to store in the fact vector is actually here, right? Actually the address of this parameter field in setup fact, which contains the CFA of dub, right, where the definition of factorial starts. So when we execute the vector stored in fact by pushing it on the return stack and invoking exit, it's actually performing a jump call to this position in the parameter field of setup fact, where the CFA of dub is found, right? And so then when the call returns, of course, we have the result on the stack. Now we can multiply it with n-1 and to get the result, right? And this, of course, completes the recursive clause of the factorial definition. So you're saying, okay, now fact is defined, how about we check it out right away and try it? And oops, that just crashed the system, right? And good that we have warm start, right? So let's use our warm start. And actually what was missing, even though fact was defined, right, it hasn't been initialized yet, right? See, we only compiled setup fact. That means the compiler actually executed the compiling word fact, right, at compile time, and all it did was it encoded the CFA of make and round parentheses into the definition of the compilee, but make has never been executed yet, right? And make is actually what sets the vector variable to the right address, right? And so we gotta execute setup fact first. And now that's also interesting, right? Because if you look at the definition of setup fact, so how come it didn't execute any of this, right? And this is because, you know, you gotta look at the definition of make, right? And remember how the return stack is being used. So recalling our discussion of the return stack and of the address interpreter, right? Before doing a call to, you know, any of these words using their CFAs, what the address interpreter does is it pushes the return, its return address on the return stack, right? So before calling make and round parentheses, right, by jumping to the CFA of make, it actually puts the address on the return stack, the return address, and this is pointing to here, right? It's pointing to the second entry in the parameter field of setup fact, which contains the CFA of fact, right? So this address is being put on the return stack, and then the call to make and round parentheses is being made. And look what make and round parentheses does, right? So it actually pops this value from the return stack and puts it on the argument stack, right? As explained in our return stack discussion examples. So then we are duplicating this, right? And some address arithmetics is being made here, right? And what this basically does is it sets the PFA, the parameter field of fact, basically the vector address of fact, to the third entry where the CFA of dub is in the parameter field of setup fact, right? So by executing this make and round parentheses code, right, we are setting up, we are establishing the right vector, right? And the vector points to dub, to the CFA of dub. Actually, it doesn't point to the CFA of dub, but it points to the third entry in the parameter field of setup fact, right? In the definition of setup fact, where you will find the CFA of dub. So this is what make does. And then when make returns, so here, right, as explained, there's an implicit exit. So it'll pop the value from the return stack and return to there, right? But since the caller setup fact left fact basically on the return stack, right, and it got popped from the return stack here, this value is no longer available, right? So when it returns, it simply returns to the stack return value which was underneath that, right? And this was basically the interpreter loop. So when make terminates, rather than, you know, continuing with what's written here, it simply returns to the interpreter loop because, you know, the value from the return stack was simply popped, right? So, but now with the fact vector variable being initialized correctly, right, and pointing to the third entry in the parameter field of setup fact where the call to the CFA of dub is, right, now we should be good and be ready to execute fact, right? Let's see if it works this time. There you go. This video is already getting long again, so the last thing that I want to do here is demonstrate the full version of DOER and make. Again, even my full version can only use make as a compiling word in colon definitions, right? But I'm going to show you a example that also demonstrates undo as well as and, right? And the example is inspired from the Brody book, which you find in Appendix B again, about DOER and make, right? Where he is explaining how to use DOER and make to do arbitrary vectored execution, right? And so I souped the example a little bit up, and so I already entered the full definition of DOER make with and undo now, and we can start using it right away. So he's defining a vector variable Joe, and the idea is that Joe will be vectored to print something, right? Set up Joe, and again, unlike the Brody book, we need a setup word, right? So because we can only use make in colon definitions, same thing as with factorial as just discussed, right? And make Joe, the vector variable is initialized now to point to this piece of code here, hi Joe, right? The call to the print string basically. And again, we have to initialize the variable correctly by executing the setup word, right? And now Joe has been defined, and we can simply execute it, and you see that it has been vectored to the dot quote print word, right? Print string word. Okay, so the next example involves demonstrating and we are re-implementing setup Joe, make Joe. This time we are using hello instead of hi. Hello Joe. And now to demonstrate and, we use and that simply prints now. So the idea of and is when similar to compiling words, right? But now on the level of the setup words basically, so that we can still perform ordinary computation right away, right? So if we execute setup Joe, we expect that also now is going to be printed, and there it is. Because remember that when we executed setup fact, due to the definition of make, and that make actually returns to the interpreter because the return value left by the caller was popped from the return stack within make, right, in round parentheses. But with and, we can actually still do some ordinary, computation in the setup word as well. So, and now of course, if we execute Joe, it will just print our the code to which we vectored it, right? Hello Joe. And then the idea of undo is simply to, clear the variable. That's it. We have now finally reached the end of the force exploration on the Microprofessor, and I'm saying goodbye. So there are still many aspects of the force system on the Microprofessor which we haven't covered, right? And some of them are highly intriguing. For example, you can use code to actually write words defined based on machine code, right? Z80 machine code. And using int, you can even write interrupt handlers in force. And that really demonstrates nicely how much of a bare metal language force is, right? So even though it has some intriguing meta facilities which you would only find in very high level languages such as Lisp, right? For example, compiling words and having the full language, the full power of force available at compile time, which you can then use to actually, extend and modify the compiler, and also compute in force itself the definitions of the compilees, right, of the words being compiled. It also shows that it is next akin to assembler and machine language, right, because it allows you to write programs on such a low bare metal level that you can even define interrupt handlers directly in force and mix in machine code and what have you. So yeah, I hope that has interested you a little bit in force, and that you might pick up a force book yourself and start reading about it. And there are many implementations for different systems, right? Also modern implementations actually, like GNU Force and what have you. You don't actually need a microprocessor in order to have fun with force. So yeah, but I'm saying goodbye and all the best for your own starting your own journey, right, into force. Until then.